Okay, now we'll talk about bases. So the definition in the book has a base is a compound that releases hydrogen ions when it is dissolved in water. All right, once again, we already know what a compound is from before. Just to refresh, it is two or more different types of atoms bonded together. And do you remember what an ion is? An ion is an atom or group of atoms that has a charge. Remember, the charge can be positive, plus, or negative. Okay. So what we're left with in our definition here is hydroxide ions. Well, let's compare with what we remember from acids. So the definition of acid was that it's also a compound, and both of them are releasing something when they are dissolved in water. But the difference is that a acid is releasing a hydrogen ion, while a base is releasing a hydroxide ion. So that's the main difference in what is being released. Let's investigate this a little further. So like we said before, something gets released when the molecules separate when they're dissolved in water. Do you remember what that's called? What that word is? It is dissociation. It's like back off. Dissociation. And that's when those compounds are going to separate. And they don't just separate, they separate into positively charged and negatively charged ions. And we're talking about when they are dissolved in water. So let's look at our acid that we talked about last time. We have hydrochloric acid, and the hydrogen ion gets donated, and that hydrogen ion is what is released, and the acid donates this to the water so that the product contains hydronium. So acid is an hydrogen ion, and if it has a charge, note up there it is an ion, hydrogen ion donor. A donor, which just means it's losing one. Okay, let's write this chemical equation again. So hydrochloric acid plus water, H2O, has a reaction, and the product is hydronium, which is H3O, and that makes perfect sense, right? Because this hydrogen came over here with water, and so now this becomes 3 instead of 2. Oh, and this has a positive charge, plus chloride ion, which has a negative charge. So that's what was going on with an acid in the chemical reaction. Now let's look at the base. So acids donate a hydrogen ion, but bases accept them. So we'll say a base is a hydrogen ion acceptor, or it gains one. That's the main difference, and here's what that would look like. So this is ammonia right here, but instead of donating this way, it gains hydrogen from water. And what is released after that happens is this HO left over from the water. That is what is released. Because remember, our definition said that a base, the definition of a base said that a compound that releases hydroxide when dissolved in water, and that's what this HO is. is hydroxide. And you can see that the extra H that we had ends up over here in this ammonium ion. And then we are left with this. This is what released, and that actually shows up in the product, hydroxide. So here's what the chemical equation looks like. We have NH3, because there's 3 of them, 1, 2, 3, plus our H2O, and it reacts and ends up with NH4 plus OH, and this is positive, and this is negative. That's what makes them an ion. And you may be asking me why I wrote OH here instead of HO. Oxygen is the more important atom left because it still has the ability to bond. HO is actually something else, so we're going to always write OH. And it's negative, so you can see the extra hydrogen came from the water this time. And then I'm left with hydroxide. So that's the difference. Base is an acceptor instead of donates. I hope that makes sense. Please message me if you have any further questions there. So let's compare them again. So acid is a hydrogen ion donor. It releases hydrogen ions when dissolved in water, and you'll see hydronium, a hydronium ion in the product. That's the H3O. So here's hydrochloric acid. This is just an example that it could be any acid. It could be different acids. Gotta draw a plus and minus here. There we go. And acid donates the hydrogen ion, and then you see hydronium, H3O, in the product. A base, however, is an acceptor, so it gains hydrogen and it releases hydroxide, and you'll also see hydroxide in the product. So here we go. This is ammonia again. So we have our NH3, and instead of losing, like up here, we are gaining, right? And we see hydroxide in the product, and there it is highlighted. So there's some differences in the chemical reactions that occur between acids and bases when they are dissolved in water. And here's just a visual of what that would look like. So both of them, acids and bases, both dissociate, right? They split apart. And here you see the hydrogen ion is what is released, H+, that's what this is. And in the base, you have hydroxide. It's this, and that's OH minus. Okay, let's look at the first review question then. Contrast acids and bases. Now, we basically just did this a few slides ago based on what's happening during the chemical reaction. However, the objective for this lesson in the book says that this is on page 184, that we want to compare properties of acids and bases. So you will definitely want to concentrate on comparing the properties of acids and bases, what they taste like, what they feel like, do they conduct electricity, things like that. Although it would be good to do both, to talk about what is released, hydroxide instead of hydrogen ion, things like that. But we want to definitely include the properties, okay? And I'm not going to write it out for you fully, the answer, but hopefully you can get some help in the answer from this video. We're going to skip ahead for a moment to question 3. Here's a graphic from the book of sodium hydroxide. And the question is, why is ammonia considered a weak base? So I'm showing you a picture of sodium hydroxide because it is a strong base. Do you see in this picture how the molecules, how everything is fully dissociated? This is a strong base. It looks a lot like our strong acid, doesn't it? Right? It is completely dissociated. It completely dissociates. Okay, let's look at the equation of ammonia, which they're telling us is weak. This is from page 186 in the book. Do you remember from the previous video what these two arrows mean? I bet you do. So let's pause for a moment and see if you can answer this question on your own. Why ammonia is considered a weak base? Okay, welcome back. Hopefully you found an answer. A hint would be, what is it that is not happening in a weak base? What is not happening in ammonia, because it's a weak base, is it is not completely dissociating, or it doesn't completely dissociate when dissolved in water. So that means a small quantity of hydroxide ions are present. And this is telling us that the reaction between ammonia and water is reversible. So some hydroxide is left behind, but some of it reacts with the ammonium ions and goes back to regular ammonia to reform. So we're not left with as many hydroxide ions as a stronger base. So this is really, really similar, right, to what happens between a strong and a weak acid. Same thing. Either it completely or partially dissociates. A strong acid or base completely dissociates, and a weak acid or base only partially dissociates. Okay, let's look at number 4. Explain how bases clean fat and oil deposits. Okay. We know that oil and water don't mix, right? So what do we know about fats or oils? Fat and oil deposits are non-polar, so they do not dissolve in water. We do know also that water is polar. This is why they don't like each other. One's polar and one is non-polar. Okay, let's take a look at this video that helps kind of explain the graphic you see on page 186 in your book.
Soap molecules can break down grease, grime, and even germs. A soap molecule has a head and a tail. It has a head that loves water, known as hydrophilic, and it has a tail that hates water, known as hydrophobic. When we place soap in water and create that lather, the soap molecules form into these little beads called micelles. If we take a closer look at a micelle, we see the water-loving heads on the outside of the beads closest to water and the water-hating tails on the inside of the beads keeping away from water. When cleaning a surface, the water-hating tail will attach to anything to get away from water. So when it finds grease and dirt on the surface, it surrounds and latches onto the dirt. And as we apply friction by scrubbing, it pulls it from the surface, causing it to float around in the soap solution. Then when you rinse the surface off with water, the grease and grime are then washed away.
Pretty cool. I do want to point out now that in the graphic from the video, the end that is attracted to water is polar, and the end that is not attracted to water is non-polar. And we just talked about in the previous slide how grease is non-polar. So the non-polar end of the soap molecule is attracted to the grease, and then it allows it to be washed away with the water. Once again, I'm not going to write out the answer for you, but if you watch the video again and take a look at page 186, I think you could come up with an awesome answer. All right, that is it for this video. Oh, but wait, what about question 2? You may skip question 2. It isn't covered in the textbook. Sometimes the textbook wants us to figure out the answer to a question based on what we've learned, even if they don't give you the answer directly. But I feel like there isn't enough information that's been provided to you. So we're going to skip question 2. All right, see you.